The Australian Curriculum Studies Association would like to acknowledge the traditional owners of the lands and the waterways from where we are all meeting today. We pay our respects to the elders past and present, and we extend our respect to all Aboriginal and Torres Strait Islander peoples here today. We value the contributions of Aboriginal and Torres Strait Islander peoples to education and their continued support of the teaching and learning of all Australians. We recognise that for thousands of years, Aboriginal and Torres Strait Islander peoples have been the first teachers, and that we are committed to continue our learning alongside them. Good afternoon, everyone, and welcome to one of our first in the series of In Conversation With. And today we are delighted to be at the home of Einstein First, a new physics project in schools that is set to revolutionise how we see physics education today. And we welcome Professor David Blair, who started all of this from his embryonic stages and is passionate about changing how we view physics in our classroom. So welcome, Professor Blair. So lovely to have you. You know, this project now is going beyond, and it's not just in WA, it's in Australia as well, which beyond Australia, which is pretty fantastic. But I thought I'd give a little introduction to those who might not know you, because you really, I would consider a bit of an Australian treasure, especially because your footprint, I think, on the physics landscape has been very significant. And we've just mentioned that it's been 40 years in this space, and your specialism is gravitational waves. You know, that's, which I think is quite a, even my head's spinning a little bit. And it was the methods of detection of gravitational waves. Is that what your original work was in?
Yeah.
Wow, pretty impressive. Yeah. And in 1984, you developed the sapphire clock.
Yes.
1990, the Gingin Gravitational Wave Research Centre. My goodness. And that was for developing techniques for preventing instability in very high optical power instruments needed for detecting gravitational waves. Wow, more a bit on that later. 2003, the Gravity Discovery Centre. And if you are from WA, well, with a visit, and if you are a tourist, has to be on your bucket list to get there. In 2010, this is the project you developed, the Einstein First. And something I haven't seen, but I'm very keen to watch, is the 2024 part of a documentary called Bending Light. Is that right?
Yeah.
Now, I am going to say I don't know very much about those words I used before, but I'm going to have a try, because that's quite a lot of specific words that are very specific to physics. But your passion really, I suppose, will be in that we change the physics education so that more people understand those words that I'm using.
Yes.
So that we're going to change that more of our students coming through will already know what gravitational waves are and all that sort of thing. Now, what I was sort of talking about before with some people was the idea that physics is quite the elite of the sciences. You have to be very, very academic in order to even access physics. Now, where do you think this perception has come from?
I guess it's really come from people like Einstein, who was a real genius.
Yes.
He thought, he just pure thought. He would solve problems one after another. He had that incredible year in 1905 when he proved that light comes as photons. He proved that matter's made of atoms and molecules.
Yes.
Heat is generally molecules.
Yep.
And
yes.
And his theory of relativity. The speed of light is the speed limit of the universe, and all that stuff all happened in this 1 year. And undoubtedly, Einstein was an incredible genius, one of the greatest geniuses the Earth has ever had. But then what happened is that the ideas were made out to be, you have to be a genius to understand it. And there were certain physicists who really played on that, because if I can understand Einstein, I must be a genius too. So I look really good.
That one. Yeah.
And so, there's a famous story of Eddington, who was the British astronomer. He was a very good astronomer, but he was a sort of a champion of Einstein's theory of gravity. And somebody came to him and said, a journalist came to him and said, I understand there's only 3 people in the world who understand Einstein's theory. And he said, oh, who's the third one?
Well, exactly. And it seems in that context, he did such a wealth of work in probably such a short period of time that the world was trying to catch up. It's ironic in the sense that we're talking about the world, but that kind of catch up took a much longer time.
But in fact, there was a guy whose book I really enjoyed reading. His name was Edwin Slosson, and he wrote a book in 1922,
right,
about all Einstein's discoveries, and it's all there, and all the language and things about time warps and stuff like that. It's all in that book. It was all being explained very nicely by Slosson in 1922. So it was being popularized already. Einstein wrote his own popular book, to explain his theory. So he was trying to get this
momentum, I suppose.
But when his theory of gravity was supposedly proven and was on the front page of the New York Times, the subheading said, only 12 wise men can understand that theory. So
exactly. No, that's really interesting, because what we're seeing, I think, and for many of the flaws it might have at a superficial level, the media have we've actually done a little bit in that space. Now, the media perpetuate the idea that physics is a very difficult subject and it's beyond, but then we've seen real success in programs like the Big Bang Theory comedy, which I'm sure has its flaws, but I think in terms of children and young people knowing about physics or seeing, especially I think in that science space, the interactions between physicists or whatever it is, I think that's been a real positive. And I think, that narrative changing that, that people can do it. But, we know science is exciting. And I think probably through the lens of what Einstein First said, how do we get children we know are scientists? So if you say to a reception or a pre-primary class to a teacher, how many of your class are scientists? She will probably, or he will say, all of them. But we're at the level as we go up through the education system where they're not.
It declines and declines and declines.
Exactly. So how do we keep children in this program for longer and get them excited? And hang on to them.
So I always believed that it was because of the ancient nature of the curriculum.
Yes.
And the fact that they were teaching 19th century science. And I've had kids say to me, in science, we just learn old stuff. And that's their expression, old stuff.
Yep.
And so what I started to do was to see if we could get the kids interested in this modern stuff.
Yes.
And the first program I did was at Rosalie Primary School, just down the road.
Yeah.
And it was called Curved Space and Quantum Weirdness.
Fantastic.
And the kids loved it.
Yeah.
And just the fact that they are being that you're talking to them about modern science. These days, they've got it all off the internet anyway. The words are out there. They know the words photon. They've heard of time warps. And things like that.
And black holes. Every child loves the idea of this infinite space that we don't know into.
Yeah. And so then, as we went on and we started training teachers and having teachers reproduce our programs, and the teachers got the same results as we did. The kids learnt it all and loved it, and but also we got the message from the teachers that it was really good to be teaching it because the kids were so engaged. You couldn't tell the difference between the kids with learning difficulties and the bright kids. They were all performing equally.
That inclusiveness,
yeah. And we realized that we had really found the right formula.
Yeah.
But then there was our difficulty still was to stop the teachers finding it difficult to think about. And that's where I had to do lots of learning to learn how to present it in a non-threatening way. Yeah. And if I said to a teacher, "Oh, we're going to learn about Einstein's theory of gravity and curved space," I won't be able to understand that. And the blinkers are down straight
Yes.
away. If I said, we're going to work with a stretch sheet of lycra and we're going to roll some balls around on the lycra and we're going to see how the theory of gravity sort of comes out of this flexing sheet of lycra.
Yeah.
That was not threatening at all.
Not at all, yeah. and that's a really interesting point you make, because I think that's in general a problem across the profession, because science has got such a fixed view from a lot of people that it's a right or a wrong, you know, and if you get it wrong, the world will collapse. And we know, especially in the math space, maths anxiety amongst teachers is incredibly high. And we probably see the same with science, because they worry they're going to get something wrong. And I remember as a science teacher always saying, if you mix up the terminology weight and mass, which everybody does, but you show enthusiasm for a subject, a child will not hold you accountable for interchangeable. It's more about how you show, and as you're saying, get them into that space. Just being there, you can then build upon, definitely.
Yeah. Well, I'm really glad that you've raised that thing about maths anxiety, because the most recent program we've been doing is what we call Maths for Einstein's Universe.
Yeah, okay.
And we're bringing maths along with the physics.
Yes.
Because that makes the maths relevant. And what one of the things we're following is Enrico Fermi.
Okay.
And Fermi, you know, he's the inventor of the first nuclear reactor, but he was a great, 20th century physicist.
Yes.
He had this expression that it's better to be roughly right than exactly wrong.
Exactly, completely. Because that's the nature of science, isn't it? Like we're always proving what we've known before is changing.
Yes,
You know, and that's a huge part of what I think your program does, because it's funny, just leading on to that, most people will claim they know nothing, or as you say, this anxiety, I don't really know. And a lot of teachers are out of field in that sense. So it's a very daunting thing. But I was thinking, if you ask anyone on the street for two famous scientists, the first one would be Einstein, and likely Newton after that, because they're probably the most ones that they are caricatured or part of the media, which seems so ironic when people don't know. But then someone would probably be able to explain E=mc² because it's been on a poster. Or that
they will all have heard of it.
Yes, exactly.
But they won't know what it means.
And I think that's one of those things.
And almost every kid, you know, or at least in every class I've been to, you know, who's heard of anything from Einstein? E=mc². You know, at least one kid in the class will know E=mc². So and yet we don't really understand it, and yet it's simple. And one of the things that I like to do is to most Australian kids have gone to Bali.
Yes,
and I say, in Bali, did you have to change money? Oh yes, we have to. You know, have to get rupees.
Okay.
How many rupees in a dollar?
Yeah.
Well, there's some conversion number, and so you have this conversion factor, and then we say, well, E=mc². It's just like this, just a conversion factor between energy and mass.
Yes.
And it's just that the number is a bit big. It's speed of light times itself, which is a really big number, but it's just a conversion equation, and really simple. And there's a few equations like this in physics that are just these simple conversion equations, but if you try to do it exactly, it's complicated. And so we do have this program where we're teaching kids, we call it Powers of the Universe.
Okay.
And Powers of the Universe, we're teaching kids, first of all, we teach kids powers of two.
Yes.
We do this by taking a paper tape measure and chopping it in half.
Okay.
And then chopping it in half again.
Yes.
And how many times do you have to chop it in half to get from a meter to a millimeter?
Okay, wow, that's a great one.
Well, in fact, you get 1/1024, which is just about 1,000th.
Yes,
And so roughly, and that's the important thing, roughly 10 times 10 chops of the tape measure, and you've got down to a millimeter. And that means 2 to the power of 10 is equal to a millimeter, but a millimeter is a tenth of a tenth of a tenth, which is 10 to the power 3. And
Yes.
so we teach kids that roughly that this connection between powers of 2, which you can do with
Yeah.
a pair of scissors,
Yeah.
and then we work out how big is an atom.
Yes.
And how big is an atom? Well, you start do this tape measure thing, and you've gone down to a millimeter. But now, imagine, because you can't do it, you do it 10 more times on that.
Yes.
And then do it 10 more times again.
Yes, exactly. Yeah.
And then you're an atom.
Yes.
And so we make the connection.
And I think that's a really important part. And I say this from experience last night, having to do my son's year 10 equations.
Yeah.
Now, I loved it yesterday because I was, this is brilliant. I didn't love it when I was in year 11, when I was a student. And the thing you just made there is because of the relevance. Like if I'm having to do chores and chores of sums, what is the point? And children will question, well, when am I going to use this? What's the point?
Yeah.
And I think that is how we get it wrong sometimes in education. We don't make that connection to say, this is what you need to know because, and not to a flippant kind of, I think sometimes we get flippant, and if we put it into a word problem, therefore it makes it relevant because we put words in.
Yeah.
It's actually the key relevancy of the concept, isn't it?
Yeah, and I think just it's being able to visualize this world that we're in, and not just the world that we see around us, but the smaller scale world and the bigger scale world, so we can know where we are in the universe, our place in the universe.
That's a really interesting point, because I was sort of thinking about that a lot of the stuff that you're doing here are quite, I'm using the term alien, probably in the wrong context, but an alien concept for a lot of people. Like it seems, because it's not tangible in their sort of head how it works. And that is probably a key thing that people get scared by. Like you're saying, we know our world around us. To think outside of that sometimes it's quite a scary environment as well. And so I think you're right. Being able to make those connections will take away some of that scary sciencey stuff which people have.
Yeah.
Now, I always love science because we use terms like exploratory, and we use terms like discovery, and it's very progressive. Well, we know that, but we see a lot of that in the media in terms of medical science or biological sciences. Oh, look, there's a new cure for this, so there's a new thing. Physics, a lot of the perception is, well, this is what we've got, this is what we know, it's right or wrong, it's static. And this project, what you're doing, is really sort of showing this kind of the growth in physics and the progression of physics, isn't it?
Yeah. But I think there are still some important issues there. And the one thing is the idea, things that's coming out of climate science, actually.
Yeah.
And climate science is tending to be bringing us bad news, more and more bad news. And I'm really concerned that we're bringing kids up in this environment where science is bringing, depressing stories.
Yes.
And we have to try to see our way around that. And the way around it is technology, I think. And there are, and so we have this program that we've developed for year 9, 10. My feeling is that at the end of year 10, which is the last year that lots of kids will do science, what would you like them to know? And I think that everybody deserves to know the story of how the universe was created, and the story about the Earth, why the Earth is like it is now, how the Earth was created. So it's like the first chapter of the Bible. Why is the first chapter in the Bible? In the beginning, such and such. It's because it's really important for us to know, and everybody should be able to share our knowledge of physical reality. And years 9 and 10 are the last years that we really have everybody in school who has to do science. So they should get that story. And at the moment, virtually nobody gets that story.
No.
And it's so sad that we are depriving everybody of this most wonderful discovery, which is the result of thousands of scientists, over a few hundred years or 1,000 years have finally, we've been creating a better and better and better story, more and more accurately, and now we've got a really wonderful story to tell, and everybody should share it.
Yes, exactly. And I was talking to someone the other day, and it was, we all teach the primary school the mnemonic for the planets and the order of the planets. And, I think when I was at school, obviously we still had Pluto on the end, and now it's been changed and people's uproar that, it was in there. And we do see that. We get people who are like holding on to things.
Yeah.
So I suppose we're, in your project, we're moving away from Newtonian physics into an Einsteinian physics. Do we throw Newton out with the bathwater?
I actually think it's very important to, in a sense, to discredit Newton. Of course, we need to understand historically the really important things that he did, but it's also really important to understand how it's created enormous misconceptions.
Yes.
Because the most important thing that Newton did was to show that that the universe appeared to be ruled by these perfect laws, these perfect mathematical laws, perfect laws of ellipses, and the planets moved in these perfect ellipses. And Einstein came along and said, no, that's all wrong. It's fundamentally, it's all wrong. Mathematically, it's only a little bit wrong, but fundamentally, it's completely wrong, because Newton had this idea that space was a sort of infinitely rigid a framework that most of us sort of imagine is out there. I mean, if you ask people to say what is space, they don't really know, except they'll think it's absolute in the sense that, and they'll think that time is absolute. And yet Einstein came along and says, no, time is different here than here. And that space is curved and light doesn't go in a straight line and geometry is all different. And so that's the reality that we know. And Newton's is infinitely wrong in relation to the concepts, even though mathematically it still works on Earth. Not near a black hole, but on Earth it works pretty well. So that's made it really difficult. And the difficulty is, is that it creates this sort of sense of confusion. Now, for example, we were teaching some Year 7 kids, and one of the things we do is we play with geometry on curved sheets of lycra, and we use little toy cars to trace out straight lines. And we show that two parallel lines, if the lycra has been bent by mass in it, which is the two-dimensional version of Einstein's gravity, then those lines go like that. How I like to say it is, straight is curved if space is curved. Straight is curved. That's sort of contradiction, but
you're right.
But you see it happen, and so it's easy. As soon as you've seen it, it's easy. So then we'll test the kids after they've done a program like this, and ask the kids, can parallel lines meet? And most kids said yes, they can, because they've learnt this program. But some kids said, no, my maths teacher says parallel lines can never meet. And so there's this conflict between what's being taught in maths, which is geometry, which is 2,000 years old, and geometry that we know today, which is one where lines don't actually meet. And it's not so hard to learn that that we can, most of the time, we can just approximate to a flat piece of paper. Only when we're dealing with big things like solar systems and things, we have to sort of worry about it being curved.
But that's a really interesting point, because when you were talking there, I'm thinking of my own education from the UK, where all of the solar system and all that was part of physics. There wasn't that separate area that we see in Australian curriculum, the earth science. And it was very different. And it's good in a way, because we look at it, there's different lenses to look at it. It's not, and we hope that it wasn't compartmentalized, that, physics inherently pulls in maths, pulls in earth science. But I think sometimes when we put things in silos, we fail to make those connections.
Absolutely. And I think it's particularly bad at primary school level, because we're starting kids off, year 3 with learning about atoms and photons and things like that, and that stretched sheets of lycra, are a model for gravity.
Yeah.
So we need to. Oh, I've just lost my thread.
Yeah, I suppose that those primary years, we probably don't give our students enough credit for their ability.
Yes, absolutely.
We kind of sometimes dumb down something, and unfortunately, science isn't given, I suppose, the allocation that maybe other subjects are until it gets further up to high school. So a lot of children probably aren't at the stage where they can conceptualize some of the, we go from I touch, I feel, I see, I wonder, and then suddenly you get to year 7, it's like, this is an atom, you've just got to accept that.
Yes, yeah.
You just got to learn it, and that's what it is.
Yeah.
So I think that's probably one of those things, and probably this is where I probably lead on to quite next, because you've already achieved huge amounts in this space, and very renowned physicist. Why are you still going? What's the passion? What makes you go, okay, this is important? Because surely you can just put your feet up now and go, I've done it. Yeah, I can tick that box. So why is this so important to you?
Well, we did really set ourselves the task of reformulating school science,
right?
And that was a really difficult, big job. And so we have this, and we call it 8 steps to Einstein's universe, and we're maybe 6.5 steps there so far.
Work in progress, yeah.
We still don't have the whole program running through. Through even there's no school who's run the entire 8 years yet, but also there are 9,500 schools in Australia. We've only got 60 schools doing Einstein First. I think I want everybody to know this Einsteinian reality, and I'll just give you one example of why I think it's really important. Almost all of us have heard people talking about how 5G phones are bad for us, and and these terrible towers and things. Well, we teach kids about photons right from the very beginning. We teach that all that type of radiation, we don't use the word, but electromagnetic radiation comes as photons, which is, of course, what Einstein proved 120 years ago. And so there are photons coming out of our phones, massive numbers of photons coming out of our phones. There are photons that we can see. Just a few are the ones that we can see. And then there are these high energy photons, which are the ones that are bad for us, dangerous. They can give us cancer and give us sunburn or whatever. And then there are the ones at the other end of the spectrum. So one of the big things we do is teach this amazing electromagnetic spectrum, which stretches over such a range, but they're all identical things, all photons. And all those photons follow one simple formula, which is just another one of those conversion formulas.
Yes, exactly. Yeah, and that's amazing, isn't it?
That Planck discovered in 1900.
Yeah.
And this wonderful little formula basically encapsulates the knowledge of every photon, from a radio photon to a gamma ray photon and all in between. And kids can visualize it and understand it. But we've also introduced lots of a language, which I really like. In quantum science, they talk about something. There is an expression that is called wave-particle duality. And that it's often misinterpreted, and it doesn't really tell you what it is. And we've turned it into a sort of child-friendly language, and we say everything has waviness and everything has bulletiness. Bulletiness has got some momentum in it.
Yes.
But if it's powerful enough, it breaks things and makes holes in things, and then it's being really bullety. But it can also be quite gentle, but it still has that bulletiness.
Yeah.
And so we teach how this bulletiness depends on the wavelength, and so everything has bulletiness,
Yeah.
and everything has waviness, and everything really means everything. In our gravitational wave detectors, we have these 40-kilogram mirrors.
Yeah.
And those things themselves have got waviness.
Yeah.
And at the limits of our measurement, their waviness sets some limits to what we can measure. So waviness is there in everything.
Yeah.
Bulletiness is in everything.
Yeah.
And once you understand that, you have a different vision of the world than if somebody says, oh, well, there's radio waves coming out of your phone, and then there's light photons, say, and thinking that they're all different. They're all actually the same, but always containing these two qualities.
Yeah. That's really interesting, because you bring that back to, this idea like the 5G. And I think we're seeing a world in which this, I talk about, before Sir Ken Robinson talks about, education post-industrial revolution, and it goes up. But now we're seeing on the cusp, especially with technology, this, absolute incredible kind of upshooting in what our knowledge framework is and where we're seeking knowledge. And I think a key skill with young students, as well as we talked about, not putting it in ChatGPT and suddenly seeing that as what it really means. And I think from a science perspective, you and I will know that evidence and data are crucial to, making sense of things, and being able to have that ability to kind of put not a skeptical lens, but have that kind of ability to look at something and go, I'm going to question this. This is right. So bringing that in, this project wouldn't work unless you had lots of research and data to support. So can you give us a little more of what you've done in that research space and how that's informing how you move forward?
Yeah. So first of all, we had to just prove to people that kids could understand it, and they responded to it, and we did that quite early on, maybe 9 years ago. And then we had the opportunity and the funding to allow us to create this sort of systematic program that went from year 3 to year 10.
Yes.
Well, we chose that age. We could have started earlier than year 3, but we wanted to finish at year 10 because that was the last compulsory year of science. So we did this. So we had to develop that, and then we had to train teachers, and then we had to have teachers teach it in school and see if we got the same results as when we, as the sort of experts who had developed it, had always been doing the teaching. And we found that the results were replicated in over the full age range. So then we knew we were on track, and we managed to sort of fit everything in so that it wasn't totally in conflict with the national curriculum as well. So national curriculum says, that you should learn about heat in year 3. Well, we say you can't teach heat unless you teach about atoms and jiggling atoms.
I was just about to say, because that was my frustrations sometimes as a teacher, because I was like, oh, they haven't really understand heat. They don't understand what it is. I sort of teach it, but I was like, oh, you could go so much deeper. So that explanation would be there. Now that's really inspiring. But what I love, talking about this project is it's not just Australia you've done it. You're moving it across the world into different places. And I suppose it's probably more reference to your research team. How do you go about the translation of terminology, of key concepts, in order for this program to be successful in other places around the world?
Well, somebody has just been translating some of our stuff into Thai. So I think it's quite straightforward, actually, to do the translation. We have a new student here who's just come from Italy, and she's been and she has already sort of replicated some of our results in Italy. And she's starting to do a PhD here, and her team, her supervisor in Torino, has duplicated quite a lot of what we've done. So we find that the replication is actually very straightforward and seems to all work really well. But we still don't have everything in place. We have a great big book called Teaching Einsteinian Physics in Schools.
Yeah.
That is a sort of foundational book for our project. We're now working on a book that's called Quantum Universe, and this is a book for teachers. So we want every teacher to have it on their desk and to be able to refer to how you can teach all these things. And that can be very easily translated.
And I think that's that kind of refinement, isn't it? Getting your research, seeing what it is, and making it, looking at it and keep reflecting on the program and just look at it. And I think that's really important. You've got researchers who are native language speakers or who are in that field in their area, because they're often, it's very easy to translate something online and go, oh, give me the translation. But when it's such core concepts, you need that ability for someone to go, oh, translated just slightly changes, or this means this. So I think that's how lucky you are to have such a research team. Now, probably a bit of a big question, and we've probably touched on elements already, but what is the long-term goal? Like, what do you envisage for
our long-term goal is that all science teaching will start with our basic understanding of physical reality, and so all children will, just like children learn about microbes, bacteria and germs or whatever, when they're small, well, they'll know that everything is made of atoms. Light comes as photons. It's just a few things, really. I don't need more than 10 fingers to put all these concepts, because the important thing is that this foundational knowledge has got fantastic explanatory power. And the idea that space is this fabric that can flex and bend and has energy in it, that is a complete change from how we used to think. But it's great to understand that. I mean, maybe it's only because it's really good to understand black holes. We've been finding all sorts of new black holes in the last few years. And we're finding black holes that are spinning so fast that they're vibrating in like crazy, and all sorts of interesting things amazing that we can have this new sense of hearing, which is the sound of the ripples of space.
Waves,
that lets you hear in detail what's going on at the other side of the universe. So that we're just a month or so away from 10 years since the first discovery of gravitational waves. About 300 black holes have been found, coalescing. We found out how gold is made in the universe. All sorts of amazing discoveries just in this 10 years. We'll soon, as this field progresses, we'll be able to listen to the whole universe. Before, from in Newton's understanding, the space can't vibrate. It's infinitely rigid, And now we know that space is a quivering jelly, just like the Earth is also a quivering jelly, with seismic waves and things. But now we have space itself is doing that. We inhabit this strange universe, which is complicated. It's not simple like Newton thought. It's complicated. We can't do the maths exactly. We can't even predict things exactly, because there's gravitational waves coming in, changing the shape of things, changing our sizes and things like that. So we are maybe in a sense not so perfect, and we're not in such a perfect universe. We're in a complicated universe, and we are, in a sense, sort of subject to that universe more than we were before.
And that quest for knowledge and this knowledge, I think it's a very safe space for people to be. Oh, I know what's happening. And, space, doesn't use the proper term, it is such an unknown, which often is quite confronting to some people because they want to know. And you kind of, as you're pointing out, that we are evolving, things are changing, we know things. And I think we, mentioned before about the anxiety that people have with science because they might not understand it or know it yet. So there's a lot of that. So if I was a teacher, and I was out of field, so I'd never done science, but I can see your vision, how do I dip my toes in to get ready? I might not be in a stage to go, right, I'm going to implement, but how am I engaging with you and your team to go, I'm not ready, but I will be.
Yeah. Well, that's where we set up these micro-credential courses.
Brilliant.
And the micro-credential courses, first of all, we brought teachers in here, and we just have small groups of teachers and sitting around and looking at activities and things, but that was not really scalable, given
the vastness.
So we had to find a better way to do it, and COVID helped us because that forced us to be to do things online.
Yes.
And so we developed an online version, and then the government came up with they wanted some pilot micro-credential courses, and we were already ready, and so we offered it to them, and they wanted it bigger and better than we had before, and so we stepped that up. Now we have capacity enrollment. Teachers want to do it. We've got teachers from around the world wanting to join the program. And it is somebody who has done no science, up except for what they learnt up to year 10, maybe 30 years ago.
Yes.
They come through our program because we have no prerequisites. We don't expect them to have any prior knowledge at all, and we take them through it. And all of the learning is this sort of experiential, activity-based learning. Like I talked about. But we have our toy atoms and toy molecules. I mean, basically, toys are the way that people learn.
Yes.
People have always, and we have no difficulty distinguishing between reality and a toy. If you have a Barbie doll, you know it's not real.
Yeah, exactly. Representation of.
But you still learn from it, and anything can represent something. So we'll represent photons with balls or bullets or
marbles,
all sorts of different things, and people can adjust very easily to it, but they have something physical to work with, and by teaching in that way, everybody gets a concrete understanding of what we're working with, and particularly, what I have really enjoyed doing is working out how to teach climate science, because people ask, why should a tiny little bit of this transparent gas, carbon dioxide, have such a dramatic effect on the Earth? There's only a few parts per million in the air, and why should it do it? And but by having introduced photons, introduced molecules, introduced
and that makes good point.
It all fits together. It all makes sense, and it's sort of logical.
And that's something, we talk about something like carbon dioxide and oxygen, and they're very familiar terms, and most people probably maybe know, the symbols for them, but they're probably the ones most common. And I remember very distinctly a child saying to me, is the oxygen we use in chemistry the same as the one we use in biology? And I remember being mind blown, thinking, oh, they haven't made that, like they don't understand. And so I think, more passionate than ever that science has to show those relationships so that overlap can be understood. So if they understand the very, very little at the very start, those other concepts can be built upon along the way.
You've really touched on something that I've been writing about recently and putting in this book, which is people have always often talked about the laws of physics, and they talk about the laws of physics and thinking, well, I mean Newton's law of gravitation or something like that, but we really do have a nice set of laws. But one of those laws is the indistinguishability of atoms of the same type. Like you said with oxygen. Every oxygen atom is indistinguishable, whether it's on another planet or the other side of the universe. That you can't put labels on anything. Oxygen is an oxygen, and that's that. You can't label it.
No, and that you made that point there, I think, which is really interesting, about the terminology we often use in science, and even the fact that we say the law gives a very finite kind of viewpoint on things, and sometimes I think that connotations is difficult.
And that's one of the terrible things that we also have to deal with, because they teach, sometimes they call it the Newton's universal law of gravitation, and then they say Einstein's theory of relativity.
Completely different concept. Yeah, exactly. You're right.
And Newton's law of gravitation was proved by Einstein to be wrong in 1905.
It's no longer a theory. Yeah, it's proof. Definitely.
So it's a disproved law that is,
yes.
It's an obsolete law.
Yeah.
But we still call it a law, and we have to change our language and get rid of that. And we should say Einstein's, law of gravitation or something, to be describing describing these things in words that are appropriate instead of completely inappropriate words.
Yes, you're right. Now we're coming to the end, which I always hate because I could talk all day, especially in your field. But the normal question we ask someone and a guest is, who was your favorite teacher? But I'm going to have a bit of a shameless plug here because as a science teacher, I recently found out that one of my past students, when I was in year 8, has just graduated and starting her PhD in, you might know more about this, the impact of solar radiation on the weathering of lunar soils, specifically the rate of degradation on agglutinates within the surface regolith.
Yeah.
And I was like, wow. And I think that moment for me was like, this is why we do it as educators. Because something like that, which I don't understand, but I know has become, someone else is going to be eminent in this field, especially. So normally I ask who's been your favorite teacher, but I think over the course of your career, there might be even a student or a teacher who might have inspired you on your journey. So have you got any ideas about who they were?
Yeah, well, I had a physics teacher here, at the lecturer here. He was, I had gone in for something called the Science Talent Search, and I won the prize, and immediately after it, he came up to me and said, "Would you like to come and work in my lab?" And he grabbed me to go to be a volunteer in his lab, and then I did my honors with him. But he always said to me, "Don't look for the easy things. Look for the difficult things, because they're much more challenging, but much more rewarding."
Okay.
And he inspired me in that way. He loved physics. I have lots of memorable occasions of him sort of bouncing into a lecture theatre saying they discovered the omega minus or something like this, and so he loved science, but he always said challenge yourself, and so that's why I got into gravitational waves, and I guess it's been worth it.
Exactly. And I think that is a beautiful way to sum up, our dreams as educators are that our students are lifelong learners, that it doesn't stop at the end of year 12, or it doesn't stop when you finish your your bachelor's degree. You still have that passion to know more and to push your learning. And it just requires that one person who's behind you, pushing you along, that can change everything, I think. So that was wonderful. And now I'll say to everyone here today, I think we'll put it on, but your list of accolades is pretty impressive. And as much as I think you'd like to help me have an infinite amount of time to, be able to change it for me to say it all in one go, but I think you have just got this vast body of information and work that really is fantastic for all of Australia. So you really are our Australian treasure, and what an honour it has been to be here with you today. And I hope this is the start of our journey with you, and looking at how many we can get more schools connecting with you and changing the physics landscape. So thank you very much.